Okay, the beginning of chapter 8, we're going to start talking about sequences. To put it simply, it's just a pattern of numbers. An infinite sequence is a function whose domain is the set of positive integers of function values a1, a2, so that's just naming term 1, term 2, term 3. These are the terms of the sequence. If the domain of a function consists of n positive integers, then it's finite. So infinite doesn't end, finite ends. All right, so let's find the first four terms of the sequence. Terms are usually n's. So if I'm looking for the first term, I'm looking for a sub 1, which is substituting a 1 in for n, which would be 2 times 1 plus 1, which is going to be 3. A sub 2, second term, 2 times 2 plus 1, 5. Third term, 2 times 3 plus 1, 7. And fourth term, 2 times 4 plus 1, 9. Okay, let's do the same thing over here for B. If I'm looking for the first term, 2 minus negative 1 to the first power. Well, negative 1 to the first power is going to be 1, so that's it's going to be just negative 1. So 2 plus 1, that's 3. A sub 2, 2 minus negative 1 squared. Square negative 1, then I get positive 1. Then it's 2 minus 1, which is 1. Third term, 2 minus negative 1 to the third. That's going to keep it negative. So 2 plus 1, 3. A sub 4, 2 minus negative 1 to the fourth. Any even power comes out with a positive number. So there's 1. This is a very good thing to know if you have a pattern that is going back and forth to the same numbers, or even just switching signs. You usually know that you're dealing with a negative 1 to the power of n. All right, one more example of writing terms. This one wants the first 5 terms. So try this on your own, come back and check. Okay, you should have been able to see some bouncing around, seeing as that we have that negative 1 to the n power. What was bouncing around was our numerator. This would be 1 over 1, and this being 3 over 3. The numerator is bouncing back and forth of 1 and 3. The denominator was just staying the same in every time. First term was 1, second term was 2, so on and so on. Writing an expression for the nth term of the sequence. Basically, we need to find a pattern. So we have to find a way to relate n to a sub n. N's are your terms, first, second, third, fourth, and so on. A sub n's are the actual numbers in the pattern, 1, 5, 9, 13, 17. We want to find the pattern for n. So let's see. How are these numbers related to n? Okay, the way I usually go about this, it's some combination of multiplying and dividing. And so I start with this first one. Okay, so if I multiply n by 1, what do I have to do to get to here? Well, add 0. So that would just be n. Does that work for the next one? Well, 2 times 1 would be 2, plus 0 would be 2, which is not 5. So that pattern doesn't work. Okay, what if I multiply n by 2? What do I have to do to get to 1? Well, I'd have to subtract 1 for the first case. Does that work for the second case? Is 2 times 2 minus 1 what we need? No. So let's do the same thing with 3. All right, let's see. 3n gives me 3. I'm going to need to subtract 2 to get to 1. Okay, so 3 times 2 minus 2. Does that work? 6 minus 2, no. Okay, let's try 4. 4 times n gives me 4. I'm going to have to subtract 3. So does that work for the second one? That would be 4 times 2 minus 3. That works. 4 times 3 minus 3. That works. 4 times 4 minus 3. That works. 4 times 5 minus 3. That works. So our pattern must be 4 times n minus 3. Okay, try the same thing on this one. Let's start with our table with our n's and our a sub n's. First term is 2, second term negative 9, third term 28, fourth term negative 65, fifth term 126. Okay, so let's try. We know this is flipping signs every time, so I'm going to have something to the effect of negative 1 to the. If I want my first term to be positive, I'm going to have to make this n plus 1, because that means my negative 1 would be squared for my first term to make it positive. And then negative 1 would be cubed for my second term, which would keep it negative. So this is definitely a multiplier. Now I just have to figure out the pattern with the 2, 9, 28, 65, 126. Okay, so we start with n's. Okay, if I do 1 times n, I'm going to have to add 1 to make it work. Well, that doesn't work over here. If I do 2 times n, I'm going to have to add 0. That doesn't work either. 3 times n, I'm going to have to subtract 1. So 3 times 2 minus 1 does not get us to 9. 4 times n, I'm going to have to subtract 2 to get to 2. This is what we're trying to get to. Okay, so 4 times 2 is 8, minus 2 is 6, and that doesn't work. Okay, so we keep going. 5 times n, I'm going to have to subtract 3. So 5 times 2 is 10, minus 3 is 7, nope. 6 times n, I'm going to have to subtract 4. So 6 times 2 is 12, minus 4 is 8, not quite. 7n minus 5 would be 14 minus 5 is 9. Okay, so does that work for the next one? 7 times 3 minus 5. Oh, well, I didn't take into account my negative 1 to the n plus 1. So if this indeed works, it would be negative 1 to the n plus 1 times 7n and then subtracting 5. Okay, when I try this over here, I'm not going to get close. I'm going to have negative. It is going to be negative. 7 times n would be 14 minus 5. I'm going the wrong way. So sometimes this strategy doesn't work, and that's okay. Once you figure out this doesn't work, I'm not going to get anywhere, basically saying I'm not going to get anywhere with this because it just keeps going on and on. Next, try powers. What if I square 1? Do I get 2? Well, if I square it and I add 1, I get 2. Now, does that work over here? If I square 2 and add it, do I get 9? No. Okay, so what about cubing? If I cube 1, what do I have to get to 2? I have to add 1. So if I cube 2, add 1, do I get 9? Yes. If I cube 3, add 1, do I get 28? Yes. Okay, we have found our pattern, and we need alternating signs. So let's put this together and see if this works. Negative 1 to the n plus 1 times n cubed plus 1. Let's try this out with a couple of them. Let's do 4. Negative 1 to the 5th power times 5 cubed plus 1. So that's going to be negative 1 times 5 cubed is 125 plus 1 would be 126 would be negative, oh, I'm sorry, it's to the n plus 1, so that would be a 6th power, so that would be a positive 1, so positive 126, which does work. So here is our formula for the nth power. We are going to learn different ways to shorten this process later. Okay, a little bit of talk about recursive notation. First of all, what this is giving you right here, this is saying that your first term is 6. K plus 1, so that's taking the next term. This would be term before K. So I take the term before and add 1. So if I'm working on my second term, I need to take my term before, add 1, and get 7. Third, term before, add 1, 8. Fourth, term before, add 1, 9. And fifth, term before, add 1, 10. Okay, another recursive. This one's talking about, it gives you your first term is 3. Term K is defined by 2 times term before K. It needs to be multiplied by 2 and then add 1. So my first term is 3. My second term is going to be 2 times 3 plus 1, 7. My third term is going to be 2 times 7 plus 1 is 15. Fourth term, 2 times 15 plus 1, 31. Fifth term, 2 times 31 would be 62 plus 1, 63. So you've got to know your notation, how to read term before, term after, and such. Okay, write the first 5 terms of this sequence. It gives us our 0 term. Sometimes sequences start at 0 terms. It gives us our first term. This says a sub k, 2 terms before, plus term before. Because if I'm subtracting 1, I'm only backing up 1. So 2 terms before plus term before. All right. First 5 terms. Well, it's already got the first 2 for me. A sub 0 is 2. A sub 1 is 4. A sub 2, I've got to take the 2 plus the 4, 6. A sub 3 would be the 4 plus the 6. It's going to be 10. A sub 4 would be the 6 plus the 10, which is the 16. And the fifth term would be the 10 plus the 16, 26.